So welcome to the pre-recording of lecture 26 of MCS 572. It's lecture 26, but it is the second lecture on pipelining. So in the previous lecture we considered what is called type 1 pipelines, where there is only speed up if you have many instances to process. In this lecture we consider two other types of pipelines where there is already speed up if you consider one instance. So you consider the big problem and you decompose it in functions. So pipelining is an illustration of functional decomposition. So I will illustrate pipelining with three important problems: sorting, prime number generation, and the solving of triangular systems. Okay, so let's look at the big picture of data archival. So one motivation for supercomputing, for using many computers in a network, is that one has a data set that is simply too large to be stored on one single computer. So here is then data archival application. We have the computers, so the processors, arranged in a pipeline, one after the other. The first processor receives new data. It moves older data down the pipeline, and the other processors receive also new data and move older data down. At the very end of the pipeline, one can say that the oldest data is discarded, but here one can say archived to tape. And archival could also be just simply a printout. This is one application of pipelining. One can adjust this idea to sorting. Here is a very simple example. We sort four numbers. At the beginning, the first processor receives 24. There is nothing there yet, so 24 stays at processor 0. Then 19 comes in. Processor 0 compares 19 to 24. The 24 is larger and gets sent to P1. 25 comes in. 25 is less than 19, so that means that this 25 is then also sent to the pipeline, and each processor receives a number, compares the number with the existing number, and sends the larger number further down the pipeline. So the sorting is here explained step by step in a sequential fashion, but the comparisons and the sends and the receives, they actually can happen in parallel. So there is parallelism here. So at the end, the numbers are sorted according to the rank of each processor. So the lower number will be with the lowest ranked processor, the highest number with the highest rank processor. So here I sorted only four numbers, but you could see that every processor will essentially maintain a bucket of numbers. The bucket of numbers will be, when it is full, will be sent in chunks to the other processors. The sorting or the inserting of new data into older data can happen simultaneously with the sending of the data. So there is the older data. One can overlap the communication with the computation. Here is the parallel version of insertion sort. Every processor does the following steps. So we are again in the model of single program, multiple instructions, multiple programs, multiple processors that execute one single program. So we make the distinction between the manager and the worker. So the manager will receive a number from standard input. So processor 0 takes it from the input, either standard input, a number that gets entered on the keyboard, or read from file. Every other processor, which has identification number I strictly larger than 0, receives a number from the previous processor. If one is at the initialization, so if there is nothing there yet, then one will initialize. Otherwise, one compares the new number to the number that is stored at the node. So the smaller number of the two will be sent to the next processor. So here the next processor, I'm running this program with a sequence of numbers that is equal to the number of processors. So there is no overflow here. Okay, so here is my example. I typed in the numbers one after the other. So the sequence of numbers equals the numbers of processors. And the messages that are being printed show the evolution of the data. So at the very end, every processor prints its numbers, and the sequence is sorted. Okay, let's do some MPI. So the manager generates as many random numbers as there are processors. The numbers are allocated in the array n. N is an array which exists only on the manager. So the manager will write the numbers and will pass the numbers one after the other in the pipeline. So the manager compares every number to the smallest number and each time sends the larger number through. Okay, so there are a number of steps. So here every processors that are further down the pipeline do fewer steps than processors with a higher identification number. So what processor 0 does, and actually every processor does this, it will compare the numbers. So the workers will receive I-1 numbers from the previous node. Will receive one number G, so G stands for a number that is assumed to be greater. So the compare and send will swap the numbers, the smaller with the greater number. Pipelined computing is another form of synchronized computing. Here for the printing, we will actually do an MPI barrier and for check, collect the sorted sequence. So this is the structure. It is clearly still within the manager-worker framework. The send and receive, it's this looks as if there is actually not that much symmetry here. So the manager sends p minus 1 numbers through. The receives actually are done one after the other by the workers. So there is an explicit loop that runs here. So there is the main loop at the top of the slide, but then there is also the implicit loop that happens because this code is executed by P processors. One manager, P minus 1 workers. Here is the compare and send. So there is one send in there that happens after the comparison. So the code is symmetric. So if the smaller number is similar to the received number, is smaller than the received number, then actually the larger number here is sent. So the received number is called gotten, which is a shorter word than received. Not entirely correct, I realize. So it gets sent to the my ID plus 1 number. And in the verbose mode, every processor writes what it is doing. So the sends are happening inside this function here. The receives are happening outside the function. So that makes it kind of harder to verify the correctness, that there will be no deadlock occurring. The other case, when the received number is smaller than the number that was stored at the processor, in that case the number that used to be smaller is sent to the next processor in the pipeline. And in that sense, there is a readjustment that is done. The received number, which was happening to be smaller, is now stored as the smaller number. So it's very also important to realize the data. So the manager node has all numbers, all P numbers in this array N. What the workers have, they have essentially only two locations. They have the smaller and the gotten. They have the number that is currently the smallest number, and then they have the number that is received. So the code is very explicit, but there are a lot of implicit locations, memory locations that are happening there. So in order to fully comprehend the code, one should actually look at the entire program, and in particular to re-examine the declarations. So we have the indices I and J. So I is the identification number of every processor. P is the total number of processors. N is the data that resides at the manager node, and that exists only at the manager node because this is only allocated there. Then we have the G and the S. So this will be the received number G, the gotten number in the function, and then there is the smallest number S. So the N is preceded by a star in the declaration because it is a reference to a sequence of numbers. But that N can only be accessed when the identification number is 0. The G and the S are variable names of numbers, and they are used by the workers. They are used by the workers and also by the manager. So the manager will pretend that the jth number is the received number. So that's the first assignment. And then it will invoke the compare and send the number through. So the j in the compare and send, that second index, is mainly for printing purposes. So we have the compare and send that does one send, and there is also one receive. So in the else loop, you can see that there is a receive and there is a send. So there is a matching send for every receive. It's harder to see with the manager in the first if statement. The manager receives, in some sense, receives its number from copying from the array. And it does one send. That is then received by the processor 1. So here you see the my ID, which is the I, and then there is the step. So the step is the J. So this program will sort P numbers in every step. Okay, so then the last is the collection. So this is a classical send and receive sequence. This program is executed by P processors. There is only one send here, but note that this send is executed P minus 1 times. And this matches the P minus 1 receives in the loop. So this is the classical manager-worker collection with a linear gathering. All right, that was our first illustration of sorting. Let's look now at prime number generation. So one classical ancient algorithm is attributed to Eratosthenes with his sieve. If one wants to generate all numbers between 2 and 21, one will remove all multiples of a prime. So it is by successive elimination. So we first look at the first number, 2. It's a prime number, so we remove all multiples of 2. The next number that is not removed is 3, so we remove all multiples of 3. And then we get at 5, and we will remove all multiples of 5. But you see already that in these two steps, we already see all the prime numbers. Can this be done in parallel? Yes, it can. So it's an example of pipelining what is called a type 2. So the array is passed through, and we will erase the numbers. So the first processor will erase all the numbers that are multiples of 2. The second processor will erase all numbers that are multiples of 3. And the erasing, so you have the number 6, which is 2 times 3 and 3 times 2. So both processors will actually mark that off, will actually wipe it out. But the wiping out, when it happens multiple times, this is not a problem. So we have, in some sense, we don't have data parallelism. So we have multiple processors that will often attempt to write in the same locations, but we do have functional parallelism, so that is important. We do have functional parallelism in the sense that as soon as a number is not wiped out, so as soon as we have not wiped out 3, we can actually ask the next processor to start eliminating multiples of 3. And the next processor 1, as soon as it sees that 5 is not a multiple of 3, is not wiped out, then it can also tell the next processor, why don't you wipe out all the multiples of 5, and continue this with 7 and 11. So this is a type 2 pipeline. So we have the type 2. We receive a prime, we also receive a sequence of number, and we remove the sequence of all multiples. And then the filtered list is sent to the next stage. So it's type 2, and not pipe 2, it's type 2. We can actually already send data through before the completion of the current stage. So the picture was not complete. The fact that things are not yet complete means that the data gets passed through, but the processors are organized in a ring. So when the data comes back at some point, the processor that was still busy wiping out numbers will actually have completed its task. So the wiping of the numbers happens simultaneously. So here you see the two-stage pipeline. When processor 1 will have wiped out 4, it will already have passed 3 to the next stage. And 9 will be wiped out, 6 will be wiped out simultaneously. So both processors will actually simultaneously start wiping out numbers. So here there is the data movement, so the marking off, but there are also computations of the multiples. So we can indicate the multiplications. So the computation time that needs to be done. So you see even with 2 processors, you have already a speed up. So if we count all the boxes, so the first processor does 9 multiplications, does 9 wipes out. The second processor does 5, so total 14, and this can be done in 9 steps in terms of 14. So we get close to we have a speed up already here. Here is the algorithm. So the input is now a tuple. Every processor receives a sequence of numbers of some size and also receives the index. When it is done, it's either the end of the line, then it can stop. Otherwise, it will start removing. So every sieving processor will determine the index that can be sent to the next processor. And then it will, after doing that, it will remove all its multiples from the sequence. So here is the ring. At any time element, so at the moment when 3 is sent at its no multiple, processor 0 will have already removed many multiples of 2, sending that through. 5 will be sent through with the partially removed numbers, then 7 will be the next prime, and 11. So by the time 11 is will be sent back to processor 0, you can see that also the sequence will have removed the removal of many of those numbers. So there is this overlapping that is happening. Okay, for the correctness, to determine, so there is a gap here. In order for the correctness, for the processor to determine that 11 is the next prime, P0 must have already removed also 8 and 10. And P1 must have been removed already 9. So there is this, before the sending of the sequence, the removal must have happened already sufficiently advanced stage. So this is the mind the gap. Okay, so the data vector is a Boolean vector. So I have no implementation ready. So perhaps this is now best to do on a parallel shared memory computer, because then there is only one copy. But however, in both implementation, you have the warning about minding the gap. So the numbers that need to be removed before passing the sequence to the next step will need to be already be well advanced enough for the correct determination of the next prime. Okay, so let's now go through the third example of pipelining. So solving triangular systems. I take the forward substitution. So we have triangular matrix. It's a triangular matrix where the diagonal coefficients are all 1. So one can think of this triangular matrix as the output of an LU factorization, where the lower entry matrix, lower entry numbers store the multipliers and the LU factorization. Then the formulas for the forward substitution can be readily derived. So it also explains why we have the forward substitution. We take the y1 and we use the value for the y1 to update the b2. That will give us the y2. And the y1 and the y2 are used to compute the value of y3. So this is the forward substitution. At first, this is a very strictly sequential computation. So here are the formulas. So this is an n squared computation, but we hope that with a pipeline we can provide speedup. So that this can be done in linear time if we have sufficient processors available. Okay, so this is the third type of pipeline. So recall what was the first type. The first type of pipeline is when we have only speedup if we have multiple instances to process. For example, if we have to sum a vector of floating point numbers. We've seen sorting. With sorting, they can already be speed up if we have only one instance, sorting and sieving. In the third type of pipeline, with the forward substitution, you see that in the later steps in the algorithm, to compute the later numbers, one needs to be more work, more multiplications, more subtractions. So the amount of work actually increases. However, the other processors can actually start as soon as y1 is available. As soon as the first number is available, it can be substituted in. Okay, so we will be using an n-stage pipeline. Here we see the n-stage pipeline. Here this is assuming that all the data is available, so all numbers, all the coefficients in the multipliers of L are available. What gets passed through is the updated right-hand side vector. So one can overwrite the B vector with the components, or here with the symbols, what actually get passed through in every step is actually the entire vector. So you see the stages clearly mapped out, all the operations. The first processor only does an assignment. The second processor does one update. Always the assignment is the last operation. So with this space-time diagram, there is obviously no parallelism and no speed-up possible. But the key is to rearrange the movement of the data. So the y1 can be passed through all the processors in the pipeline. So when processor P0 receives B1, it passes B1 to P1, P1 receives it, passes it to P2, and then starts to do the update. P2 receives Y1, starts doing the update after passing Y1 to P3. So you have this transition here. So I have two space diagrams. So there is the space diagram which focuses on the numbers. So there is the Y1 that get passed through in the pipeline. When Y1 is passed through, it takes two cycles. So P1 receives Y1, does a multiplication and a subtraction and an assignment, and then sends Y2 through. Y2 gets sent through. And you see that the operations can overlap. So as soon as Y1 is received by P1, then P1 can do already one multiplication. P1 also sends the Y1 too. So in the next step, so the multiplication already happens, executed by P2. So there is this starting of the updates. So the multiplication with Y1 happens as soon as Y1 is received. So you see the speed up that can happen now, as there is this delay from the receiving of Y1. So it's still unfortunate that P3, which has to do most of the work, receives its data last. But in the other hand, so you can see that there is there is a speed up possible. Let's compute it. So we can count the steps for p equals 4. So there is a latency. So in general, it takes 4 steps for y1 to be at p4. So we have n steps there, or n minus 1 steps if you want to be very, very precise. Although the n also counts the multiplication, so that is the thing that actually really matters. Then we have additional steps for the end. So these are the 6 additional steps for P4 to be computed. Notice the regularity here. So it each time takes 1 multiplication and 1 subtraction, and also the accumulation of the result in a register. But by then the next number is available for the last processor. So the 6 is then generalized to 2n minus 2. So we can add to the 2n minus 2 the n for the pipeline latency, and that gives us 3n minus 2 steps to solve this upper triangular system. So the total cost is n square. So we have reduced the n square computation into an n stage. So by reasoning via the pipeline diagram. So in the next lecture we will see an OpenMP implementation that gets quite close to this, and then I will also explain how to solve in general linear systems in parallel. Here we followed very closely the substitution formulas. So we didn't change the algorithm. In general, it's actually much better in parallel numerical linear algebra. One considers tiling. So one can introduce a lot more parallelism by seeing the linear system as a block structure. Okay, so this concludes the pipelining idea. I was following the book of Wilkinson and Allen. So we had one message passing implementation. I hope that this message passing implementation can be suitable for a shared memory implementation. So write a pipeline sorting algorithm with OpenMP or with Julia. Again, the insert sort can be used. Of course, we have also seen task-based parallelism. So one can, quicksort is based on recursion. We have the Fibonacci numbers. So there is actually, when we introduced tasking, so there was the sorting with tasking that gave parallelism, where one breaks up the sequences in chunks and then one merges. I have indicated the pipeline sieve algorithm. So the most difficult aspect there is the minding of the gap. So one has the slowness of the communication versus the number of multiplications that must be done before sending the next sequence through. So this depends on the number of processors. So if you have only 2 or 3 processors, then the gap is not that large, but the gap will become larger than when the number of processors grows. Note that the goal of this exercise is to write a correct message passing program, but actually you can already compute the gap independently before you start thinking of message passing. Actually, the gap is computed how many multiplications you need to do before the gap comes, and that can be done via a purely sequential operation. So it depends on the number of processors, but actually probably also on the on the size of your sieve. That's another possible. So there are the distribution, the gaps between the prime numbers. So you can look also in the literature what is the in number theory, what is the gap between the prime numbers. So in some sense you can do this experimentally, exercise 2, but also via referring to the literature. The pipeline sieve algorithm, one can also implement this with shared memory. We've seen how to formulate the task dependencies both in OpenMP and Julia. So this is another illustration of the need to formulate this. Can you do it? Actually, that's the question. Could be no. But if you refer to the literature, it could be yes. So I did the lower triangular system, try to do the upper triangular system. Here it is different if you think about the LU factorization, where the diagonal elements are not 1. So it is different in the formulas in the sense that you also have a division still that's happening before the final assignment. The purpose of this exercise is also to draw the pipeline in great detail. So the main concept that we have seen in this lecture and the previous lecture is the space-time diagram, which allows to visualize the parallelism. So that is the tool here that was introduced to analyze pipelined computations. Okay, thank you for your interest in this topic. I hope it was interesting. Next time we start parallel linear algebra, going more deeper into the topic of solving triangular systems in parallel.